In the previous lecture we talked about functors, and I hinted that there was some deeper mathematical theory behind the functors. It wasn't just some ad hoc invention with a map function which allowed us to sort of transform the contents inside a container type into something else. And in this lecture we're gonna look at a little bit more at the details of what a functor really is and where it comes from. And in order to do so, we're going to need a little bit of category theory. Category theory is a fantastic mathematical theory which allows us to study the structure of things. It's really an amazing way of abstracting things. Just look at the pure essence of some underlying thing without looking at any of the details. And for that reason, it's also a very abstract mathematical theory. And when it was invented back in the 50s by Saunders Mac Lane, it was criticized by mathematicians for being overly abstract, which says a little bit about the theory. But then people figure out that, hey, this is actually truly useful and practical and not at all that difficult. And the basics of category theory is quite simple, but of course, with everything that mathematicians touch, it becomes very deep and complicated in the end. But we're just going to look at the surface and see what is category theory, because that's easy to understand. So when we started talking about functions, we talked about sets. We had a set, and in the set we had some elements. I'm just going to call them A, B, and C. Right? These were some things that we put in, maybe sets of integers, sets of whatever we might decide to put in there, and we can look at them. And we call these things elements. And then we could have two sets, and we could define functions from one set to another. So we could map an element in one set over to another set, and so on, right? So in category theory, it's much more general than a set, but we don't really have to care. So we can think about categories really as sets for most of the time. But what we do in category theory, in set theory, we put these elements in, and we know what they are, and we know what properties they have, and we can play with them, and we know everything. In category theory, we take these elements and we put them into our category and immediately forget what they are. We don't know anything about them, anything at all. But what we have in addition is that we remember that we had functions. So we knew in the other way, in the set, that we had a function from for example, from A to B. That's an F. And from B to C, and that's called G, for example, so we had some functions. And those we also put into the category. And we just call them objects. So instead of elements, we just call them objects. And A, B, and C are objects, and so are F and G. We often call these functions, which we don't really know that they are functions anymore, because we don't really know anything about them. And after we call them a category, we forget everything we know. But these arrows, these are functions. The stuff that used to be functions in the set are now called arrows or morphisms. But from a category point of view, it's just some relation between A and B. It's just an arrow between those two things, and that arrow is an object of the category. So you already see now that we are starting to we don't really know what we have. We just have structure. We know that we have some dots and we have some arrows. And in order for this to be a category, there is a rule. And that rule states that if there is an arrow from A to B and there is an arrow from B to C, there must, in order for this to be a category, exist an arrow from A to C. and that we can call f before g. This is just a composition, and that's it. Now we have basically defined a category. There's one little thing that is required, and that requires that there's an arrow from C to C, which is called IDC, and there's an arrow from B to B, which is called IDB, and there's an arrow from A, and that's IDA. So these identity arrows. Remember, we had a function called identity, which had the signature, which we could implement like this, ID of x equals x. So it doesn't do anything. So these are kind of sort of trivial arrows, but we need to have them. Right, so what we have here is that now we have three objects and two arrows and their composition. And that defines a category, and I'll call it C. And for this reason, really, category theory can be called the theory of composition. Because that's the only thing we really have. The only thing we really have to grab and we can hold on to is that we know that we have some objects and some arrows, and we know that they compose. And everything else is derived from this property of composition. That's category theory. That's the definition of a category. And yeah, it's pretty abstract. Because that's exactly what we want. We want to get rid of all the details. We don't want what we're dealing with, just the structure. And this is the structure. All right, so functors. So now we have the category C. So suppose now we have a new category, which I will call, put it here, and I'll call it D. Some other category. And now imagine that we have some function type like thing, which I will call f, which when I apply it to any of the elements or any of the objects in C, it moves them over to another category D. So if I say f on this A here, it gets transported into this D as FA. Or if we like, we can also call this A prime. Right? And I can do the same thing with B. FB or B prime. Or BD or whatever we want to call it. And of course FC. And then I need to be able to take this arrow, which I could write this F here. F I can write as arrow between A and B. Yeah? So now there appears the arrow. Right? So now I can say, okay, F, if I try to move F from here, I could say, okay, apply F to that thing, and I need to get an arrow in here, which must be the arrow FA to FB. And the same goes for FB to FC. And then we have the composition. And if I apply this F, capital F here in between, so if I apply it to that thing there, that means that if I had the composition of F with G, I need to have the same thing here as F of F with F of G. So look, this function F, we'll just look at that one there, this FA to FB, that we can also call just F prime. And then, of course, this here would be like f prime composed with g prime. Right? So now we see that this thing here, f, that's the functor. And we'll see in a moment how that's related to what we already know. Right? So what the functor is a function from one category to another. So in set theory we had a function from a set to another set, the domain to the codomain. The functor is now a function from a category to another category. And that's it, really, for functors. And of course, then we need to, there's one more thing, of course, we had these identity arrows here, so they need to be so we had IDC, so this would be IDC prime in this category. So we need to have the identities. So all the pieces that we have in a category need to be transported over to this new category D. Now, this new category D can, for all intents and purposes, be the same as C, which is a very common situation. And in case that is, we are just mapping to from the same category, from one category back to the same category, then it's called an endofunctor. So if you're reading literature, you will see that they are talking about endofunctors. That's just functors from the category back to itself. All right, and we're going to be dealing in programming. We're mostly interested in the category of types. So the things that we have here are the types, and we will see how this works in a little second. Right. So what have we found out? Well, we have found out that if we have an f, and it takes which basically takes an a and produces an fa. And we have a f which takes an a to a b and produces an fa to fb. Yeah, so it transforms simple objects to this other category. It transforms functions, or these arrows. For us, they will be functions, but it will transform arrows from one category to the other category. And we have this other f, which takes the composition of two functions, f, g, and transforms that into f, 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 g. And then we have the final thing with this functor does is that it takes the ID arrow and transforms it into FID. Right? These things here are called the functor laws. And what we will do next is we will take the option type and see how it sort of fulfills the functor laws, and see how these fairly abstract concepts with these categories and things, how they actually are related to the types that we are using and to the generic types. Okay, that's the plan. So we're going to go through piece by piece through these things. Okay, let's start with the first one. So let's write up the definition for the option type. Type option A equals sum of A or nothing. So this is what we're working with. Okay. So how in Earth is this related to that? Well, we can look at this option of a generic type here. We can actually look at this as a type function. It's a function which generates a type. Normally we have something generating a value. So we say that, well, integer 5, and we get an integer of 5. That's a data constructor. But this is actually a type constructor. Right? So this we could write this sort of in pseudo syntax as a function option, which takes a argument a, which is a type, and it produces a option of a, which is a concrete type. So this option here is a function to produce a concrete type. And now if you look at the structure here, and I can write this like this, we see that there is a very clear similarity between these two things. Right? So, how does this work? Well, in order to create an option of some type A, I can actually use my data constructors. And I have two of them, so I can say sum 42, and that will of course have the type option int. So what happens here is that this sum here is a function. It takes a type integer and creates the integer option type for me. And it also creates the data. And of course I can say nothing and give it an explicit option int, and I can create the nothing value of the int type. So this is how I suddenly created this f side of things. Okay, so those were the values. Check. How about functions? Well, we can try. Okay, so I have a function, I will say call it from A to B, and now I want to do this with it. So let's try. What happens if I do sum f? What type does that have? Well, that turns out that it has the type option A to B. Now, okay, that is not the same as this. This is something else. So that didn't work. So we can't use sum to transfer the sort of the arrow or the function, transform that into this functor. So we need something else, because this is not what we have. And of course we know already what the answer is. What we need is a function we call map, which takes the function f and it takes some value x and transfers the over here. But map, let's look at the signature, how this works. Map, it takes a function A to B, it takes a value of A option and a value of B, produces value of B option. As we showed in the previous lecture, if I have an option containing 42 and I can apply some function, it will change the inside of it to whatever, turn it into a string or option or something. Right. So how does this look? I should probably rewrite this as A, B, 2, then it's clearer what's going on. So if I take map here, we know how this works. Like we have used this on lists. We have a list or an option containing some value, and we apply a function to it, and we get out a a new function, get out the new list or option where the value has been transformed. But if we partially apply map, so if I would partially apply map, so I now give it the function, what I get is a new function takes an option of A and produces an option of B. Now look at that. That's exactly what we needed, right? So now we see that we can think about map in two different ways. One way is that we say, okay, map is a function which takes a function to transform the contents of some container, and you give it the map, the function, and you give the container, and it spits out the new container with its contents transformed. That's one way of looking at it. The other way we can look at it is say, okay, map is a function which transforms a function from normal values, A and B, into a function which accepts these sort of lifted values, these embellished values like option and list and so on. So it's actually not transforming the container, but it's transforming the function. Two different ways of looking at the same thing. And you can choose whichever you find more natural. All right. So we've seen that. So now let's look at so that's a check. Next, let's look at the identity. So I've already done all this stuff with the option map, implemented map and so on, so I won't do that again. But let's look at how does this work for identity. So what this states really is that the ID, if we do map ID, it should be the same as ID. So if I map with ID, nothing should happen, right? That's basically what this states. And let's see if this holds. So we can start with the nothing case. So I can say map ID onto nothing. So now, and remember, ID is this function which ID of x equals x. And one of the things that you should remember from the previous lecture is that map of whatever or nothing always produces nothing. So it doesn't matter what I put in here. Map whatever or nothing will always produce nothing. Now, of course, nothing here can be rewritten as ID of nothing. Since ID applied to nothing, ID nothing is nothing, right? So I can sort of just expand nothing by adding ID or applying ID to it. It doesn't change anything. And now we can do what we called in the lambda calculus the Eta reduction. And lo and behold, we have just showed the nothing case of map ID. Okay? So let's do the sum case. Map ID onto some x. Well, we know that this is equal to some ID x, which is the same as some x, which again is the same as ID sum x. And again, Eta reduction, and we have shown map ID equals ID. Check. All right, so now we have covered that case, and the identity case of the functor laws. And what now remains to be shown is that the composition behaves like this. So let's look at option and see how the functor composition works. And again, we're going to start with the nothing case because that's simple. So what we want to show is that map f composed with g is the same as map f composed with map g. And the first thing we do is a map f g apply it to nothing, and that is, surprise surprise, nothing. Since map whatever on nothing will always produce nothing. And now we're going to do a little trick like we did with the identity. Nothing can be written as, well, I can write nothing as map f nothing. That's still nothing. And nothing equals nothing, so I can, you know. And then I can rewrite this nothing here as map g nothing, which is still just nothing. And of course now I have map f of map g of nothing, which we can write as map f map g on nothing. And now we can do from lambda calculus Eta reduction, zap, and now we have map f composed with g is the same as map f composed with map g. Useful transformation, which allows you, when you're actually writing real code, allows you to sort of flip between these two if need be. Sometimes you end up with this form, and it's actually much more convenient to write it like that. Okay, so that was nothing, and that was nothing. So now let's turn to sum, and that's quite something. Sum is slightly harder, but not much. All right, so we do map f g on sum x. What is that? Well, that is nothing but else but sum f g applied on x, which of course is sum g f x. First we apply f, then we apply g. Okay, so what can we do with this? Well, we're going to do a similar trick as we did with nothing, but now we're going to sort of do a mental unmap. So this is essentially just some value, and we apply a g inside a sum, which means that this can actually be written as map g on sum f x. So if you perform the map here, you will see that, okay, map will apply g to this value here. So we just did the unmap. And again, now I can do the same trick with f. So this here can of course be written as map f on sum x. And now we have map g, map f, sum x. And this is of course, now you see that the g's and f's are kind of swapped here, but that's just because f is applied first and then g, which is actually the same as saying map f map g on sum x. I could of course say map g map f sum x. So I can just flip those. Just forward and backward composition. They're the same. And now we see that map F composed with map G on some X. Well, Eta reduction on that thing. And here's the result. And we have shown this thing. QED. And yeah, so now we've shown that the functor laws hold for the option type. And if you create your own functors, you should really check the functor laws, but most of the time you don't have to, because you need to do some weird stuff in order to break them. But now you know how to do it. And it's not really hard. It's a bit of work, but not much. And actually an easier way to check them is that you just pull out F#, you write down your map function, and then you just check, just write down exactly like this and see that they hold. So you can check the identity and you can check the composition. So you can just say, well, map G, map F composed should be the same as most. And if they're not equal, then you've done something wrong. So you don't have to even have to go through the manual labor of showing that the functor laws hold. You can just use the compiler. So that's, now we've shown the functor laws for option. And of course, this is something you don't normally do in every day, but if you create the new functor of some new fancy kind, you need to check these things just to make sure that you haven't done anything stupid. And as I said in the previous lecture, if you have a for example, a record type and it contains some other auxiliary data, and then it has this generic A in it, container A, your map is only allowed to touch the A. And what you can do is that you can create a type where you actually modify both, and then you will see that the functor laws won't hold anymore. And then you break them. So that's actually, that restriction comes directly from the functor laws. Okay, so before we conclude this session, we could look at a little bit at what this functor stuff is about. It's just a mental picture, really. So we can think about two worlds. We have a world of, down here, of simple types like int and string and list. And it can be like, or well, list is not, int and string and float and pairs and what have you, right? Actually, we could have a list here as well. We can have functions, we can have all kinds of things. But we're down in this world here. And what happens is that when we apply a functor, is that we lift these things into the world of this functor type that we're interested in. So what happens is that we do this lift. And this is a word that is used a lot in the literature, lifting. We lift the integer, we lift the string, we lift the float with this thing up to this world up here as ints, as strings, as floats, and so on. But this is now in the world of option, or list, or just F for general functor. Right? This means that, like, this is just essentially saying that given an integer, I can put it inside an option, and it becomes this elevated thing. And then I can lift the functions using map, so that they start operating on this upper world. And then, so then that means that whenever I have a bunch of these things, options or lists or whatever, I can take normal functions, I can lift them up to that world, and then I can just start applying and composing them in this upper world here. And this is a good mental picture, because what you can easily happen when working with functors before you have been used to them, is that you have some stuff here, it ends up inside a option type, and then you extract stuff, do things, put them back in, and you start zigzagging like this. Which is just unnecessary code and complexity. So what you can do, of course, is now that once you go up, you just lift anything you need, you lift them with map and so on into this upper world, and you just compose everything, and then when you're done and you need to extract something, you come down. So that's one way of looking at, also looking at functors from a slightly different perspective. Yes. The final little thing we're going to look at, maybe in the next lecture, yes, a bit more, is that map can be generalized. So now we had created a map, which was took a function from A to B, but we can also create something like map 2 or map 3, map 4, and so on, which takes functions like A to B to C, and of course 3 arguments, 4 arguments, and so on. And it's quite easy to generalize these things. I think actually in F# also these things are called, not called map 2, map 3, they're called, but I'm not 100% sure about this, they're called lift n. And we're going to see more of those in the next lecture. Right, so that was that. That was all about functors, and now you know everything you never wanted to know about them. In the next lecture, we're going to look at something called the applicative functor, which is a slight twist of this game, and is my absolute favorite abstraction of all time. Until then. So there was a question, a very good question indeed, and the question was, what would the consequences be if we create the functor but we don't check the functor laws and they don't hold? What's the consequence of that? Well, the consequence of that would be that for example, suppose now you have a function like x squared and you apply it to an integer, and you expect to you say 5 and you expect to get 25 back, and then you lift your function into this world of options or lists or whatever you do, but you just lift this and you give it 5 and you expect to get 25 inside of a list or an option or a map or whatever. But if the functor laws don't hold, that's not necessarily true. You might get something else. And then you can see that that's not good. So basically what you should have is that A to B should be sort of equal to FA to FB, where this F just carries some extra structure, extra information, some kind of side effect. But the A's and the B's should definitely behave the same way, that the value that it contains should be mapped by this. But if you break the functor laws, all bets are off. Well, maybe not all, but some at least. The same goes for the composition. There's no guarantee that the composition of these things will work at all. So you might have a situation, even I think you can probably come up with a situation where this holds, but you break the composition. And you can also break the identity. So you can say, well, all of these are the holds, but then the identity suddenly is broken. And that's not good. And we'll see more about, a little bit about the importance of identity when we talk about monoids and monoid homomorphism and the like stuff. So that was a very good question.